All right, thanks everyone for coming. People are still slowly joining this webinar, but let's start. It's a pleasure to introduce Diego Bagnis. Diego is the Chief Scientific Officer at Oninn in Brazil, specializing in organic photovoltaics, perovskite solar cells, and organic sensors. Diego holds a Ph.D. from the University of Perugia in Italy and worked at the Northwestern University and Konarka Technologies. With over a decade of experience, he focuses on scalable fabrication techniques for PVs with the primary goal of bridging research and industry. With Diego's talk, we are going to learn more about the challenges that we face while bringing OPV from the lab to industry. Thanks a lot, Diego. Thanks for accepting our invitation, and please, let's start.
Yeah, many thanks, Daniele, for the nice introduction. It's a pleasure to be here today. Yeah, as you announced it before, so we try to enter much more. It's clear it's necessary some research and some development, but it's slightly different than the basic research from our side. And so just to try to enter slightly more, what I believe will be one of the first, if it's not the first, OPV panel in the market based on the non-full arena acceptor. So just to give a small introduction for who doesn't know the Oninn. So in this case, we are a private research institute where we try to make a bridge between the basic research and the market. This means that for in several technologies that maybe we believe that are in the stage of the proof of concept that are not still ready maybe for the market, we try to prototype in the proof of concept and demonstrate to the market and for the new investor that this can become a real product to apply in the market. And this happened, for example, for OPV in 2016, where was co-founded the SANU, that is our spin-off. And so our specialization is much more on the prototyping, and so to try to demonstrate the average value and not the best performance in the production or semi-production environment. Just to give as well a small overview on the technology readiness level that we are, as you mentioned before, Daniele, so we are not only working on the OPV, today we are speaking much more on the OPV, but we are working as well on the scale up for the perovskite. We have already some panel of the perovskite. It's necessary to dedicate much more time in order to improve the stability, and we recently gained as well a pretty nice grant for the next 5 years in order to stabilize the lifetime. So for the OPV, it's clear that we are much more close for what is already a product applied in the market. It is a several years we continue to apply our panel in the market in order to understand slightly better so the behavior in order to find the right solution for the customer request. So as I mentioned before, it's clear that when you try to scale up, so it's not only to improve or to increase the dimension, but there are several conditions around that are connected to the financial side. And so it's clear that when you try to make something that is possible to produce in a production line, it's necessary to avoid, for example, the halogenated or chlorinated solvent in order to try to using just green solvent. In the other side, to avoid as well inert atmosphere and to try to use in the air conditions, so the lab condition in general, and as well to speed up as well the production during the day will be appreciated much more to using the flexible substrate. In the other side is to try to reduce at minimum the temperature usage, because all these kind of parameter has an impact directly on the capex. That's is the capital expenditure, so the money that you need to create the factory. And the other side as well, that is not less important, the OPEX, that is the operational day by day. So in the other side, it's clear that everybody probably working on the PV by coating know the golden triangle where it's necessary to using the efficiency, cost, and the lifetime, and so to try to find solution that enter inside of this triangle. It's also true that when you move for a production, it's necessary to increase and to give an additional corner in order to have as well an yield. This means that your solution have to find a way that when you coating, for example, 100 meter and you are able to use in just 80 meter, this 20 meter that you trash enter inside of the cost of the 80 meter that you sell. And so it's clear that to improve the yield is another fundamental part that tendentially not entering inside on the development. In the other side as well, for the product issue, connecting enter inside for the warranty or the reliability, and so in that way is an additional corner from the original corner of the triangle. What I want to say that tendentially the people thinking that is necessary to start in here in order to arrive for the final product. From our point of view, we want to see what will be the final product in order to develop directly in the R&D for all the characteristics, not only the material, but as well to cover the cost and the lifetime, because we see later that maybe not all the issue are connected to the lifetime, that normally is the question arriving connected to the OPV, but depending on the application, and so what you want to do with this kind of panel. From the application, as I mentioned, so as I mentioned before, so will be so from the PV application to R&D and not reverse it. And so we can see here that so there is I try to divide in a two big blocks. So one is the technology development and the other the market development. So it's clear that you are looking for a panel that's entering inside what we call normally dollar per watt. And so in that way that you need to have a cheaper panel with the higher value, intrinsically a higher value, is clear that you compete not only with the silicon, but every kind of energy. And so in that way is a pretty high challenge connected to this kind of market. In the other side, there is as well what I call kilogram per watt or gram per watt. So where there is an additional value enter inside on the account of the panel, where there is the weight. Just to remember that a panel of OPV and as well the future for the flexible perovskite, we're speaking about half kilo per square meter. And so comparing to the silicon, tendentially is around 20 kilogram per square meter. In the other side, what I call it as well application per watt, this means every kind of application where the energy generated is not connected to the value of the energy, but is connected to the solution that you have connected to the application. For example, the Internet of Things, a sensor or whatever. In the other side, so it's clear that from the technology development, so this means as well connected to the outdoor, maybe the mixed red light, indoor low light, where there are different other solutions, because maybe here you don't need, for example, the UV cutoff, because there is as well a part of the light, or there is much more diffusion light, and so there is not a direct maybe ultraviolet part of the light. In the other side as well, the low light, that's are different market where a different characteristic, as I mentioned it as well, for not only as well the quality of the barrier could be much less because the exposure. So if you are using in indoor, there is less variation of humidity as well less variation of the light with a stronger light. Just to enter much more in the status of the evolution, just a brief overview on our device, especially for the results that I will show later. So our standard cell is a 5 by 5 centimeter on flexible substrate, and tendentially there are 8 individual cells, something more than half square centimeter. From the module side, our statistic is much more connected to this mini module that is more or less tendentially 3 centimeter by 110 centimeter wide, and we're speaking about 6 cells connected. So everybody know that's working on OPV. So in general way, there were a big step forward connected to the development of new donor material, especially for the low band gap donor. But it is also true that in the last 7-8 years, the big step forward, especially for the OPV, that arriving for the Euro cell over 20% or around 20% now in the literature is clear, not in the condition that we are working, but in the standard condition for the lab and for the research, the basic research development. But it's clear that the big step that give forward the non-fullerene acceptor was pretty clear. And it's pretty interesting because to using this kind of acceptor combining as well with the donor is possible not only to have a great results, but as I said before, in order to tuning maybe the performance based on the application that you want to achieve or the application that you want to apply. And so it's possible not only to have a different current, but as well different tension, and the other side as well different characteristics, especially for the F factor. That is one of the tricky part, especially for the scale up, because it's one of the first parameter drop down over that there is the value of the power generated. So it's clear this seems pretty simple. You take the material, you try to apply, you try to develop whatever, but it's not exactly so simple, because it's clear that when you start to using the non-fullerene acceptor, it's not possible to using anymore maybe the material that you was using with the binary fullerene acceptor like a acceptor. And so in that way, it's clear that in our process, tendentially our layer are coated by slot die, and tendentially we have as well the top contact based on the silver using the screen printing. Just to remember that the screen printing is the only technique, is the cheaper technique, and so is really appreciated to using, especially from the capex point of view. But it's also true that is the technique that there is a contact for the deposition of the silver. And so it's clear that as well, if you tune in this contact, there is this contact. And just to remember that we're speaking about a layer that are few nanometer, few hundred nanometer. And so it's clear that the issue of the HTL tendentially, so if you try to use maybe the molybdenum oxide by evaporation, we're speaking about a few tens nanometers. And so this, to using this technique, create creeks and create shunts. So in some way, it's not possible to use a thinner HTL. As well for the PDOTs, if you are using just really thin HTL, you are not able to use in this technique. And so you lost a lot of, or you reduce the performance, but you lost as well a lot of sample. So it's clear that one of the challenge was exactly to improve the HTL and to achieve over 300, 400 nanometer in order to continue to use the screen printing. And the other side as well, to using the new material, the donor material with the non-fullerene acceptor, tendentially you improve as well the absorption coefficient of the photoactive layer. And so in this way, tendentially the thickness of the photoactive layer is much thinner than the standard one that tendentially normally is around 300 nanometer. And so with the non-fullerene acceptor, tendentially this is around 100, 120. That is really, really thin. And why this is an issue? Because when you move for the slot die, this can create a shrinking or create a defect connected to the coating. And so tendentially will be appreciated and will be great to have a photoactive layer over 200 nanometer, or at least 200 nanometer, in order to reduce this shunt and this defect during the coating deposition. So just to give us brief overview as well what I mean when we're speaking about binary ternary. So in this case, it's clear that, for example, the binary, you can see that tendentially you have the non-fullerene acceptor and the donor. And as I mentioned before, you can see with the standard molybdenum oxide, you are able to achieve pretty interesting results, close to 10%. I just to remember that we're speaking about a green solvent working in air on the flexible substrate. And so in that way, you have already reducing the performance. And so this close 10% is a pretty nice result in the condition that I mentioned. But you see that as as well with the standard PID or the standard HTL Solar One, so the performance drop because it's not aligned with the energy level with the material. But to modify, and this was a work over close to 2 years, in order to modify as well the PID and to gain in some way and to arrive close to this performance. In the other side, it's also true that what is pretty famous as well, the non-fullerene in the beginning was the lower cost because it's a small molecule. We're reducing the cost of the synthesis and as well the purification over to avoid the polymerization of the material. In the real case, it's also true that the non-fullerene acceptor tendentially are pretty complex small molecule and the cost of the synthesis is pretty high. And so tendentially, the only way now to reduce maybe this kind of cost is to try to reduce the quantity of the non-fullerene and to try to improve the performance to gain with the non-fullerene. And so you see that, for example, we arrive at pretty close results as well with the ternary. Later we can see some more results in detail. Another part, and I believe is pretty interesting, this is how is the behavior as well of the temperature during the coating. These are the blade coating results by non-fullerene acceptor. And it's pretty interesting that when you reduce, in our case, and with our condition, to reducing the temperature, so it's pretty interesting because it's not only that you improve the performance slightly, but you have as well a better standard deviation in standard deviation in the results. And over this as well, if we try to compare two different photoactive layer thickness, so 250 nanometer and 50 nanometer, you see that is also reduced the gap between the results comparing the temperature. What means this? That we have much more tolerance in the variation of the coating during the coating in the web, and so means higher yield. We have some slide dedicated for that later. But just to show that was pretty interesting this, because going exactly in the direction, because if we reduce the temperature, not only we get a better results, but it's also true that we reducing the CO2 producing for the creation of the panel, and so these are positive impact as well for the energy yield created. In the other side, so when we take these results and we try to move for the roll-to-roll slot die coating, we are still speaking about on the roll-to-roll in the R&D. We have several equipment, but here is still in the R&D. So with the fullerene acceptor derivatives, we can see that to change the thickness, and one of the parameters that we have tendentially to working on it is to increase the concentration, because tendentially so the formulation created on the blade coat is not the same used in the roll-to-roll for several reasons. One of them is connected to the fluidodynamics involved. Just to remember that the blade coating, you have the substrate fixed and you have the movement of the head, and so the meniscus created is slightly different compared to the slot die, where you have the web is moving and the head is fixed. And so in that way, tendentially is necessary to increase the concentration, and you have some limitation. As I mentioned before, when I speak a limit about the 200 nanometer of the thickness, sorry, you see that, for example, 140 nanometer, we see coating defect. And just to show, for example, here in the table, you see that we have a lower results. Here in the graph is not mentioned. And what is pretty interesting for this formulation in this condition, if we have a 200 nanometer already, and we improve till to 50% more, and so to arriving to 300 nanometer as well, the performance not changing too much. It's clear there is a better performance, slightly better performance, but in the other side is pretty stable as well, the performance and the other characteristic. And this is pretty interesting because this give for the production a pretty more insurance in terms of the results and the coating and the number of panel ready to apply directly on the client, on the application. As I said before, the yield is one of the main parameters, just to show a couple of graphs about that. So here we're speaking about in the best condition with a dirt substrate, with the higher concentration at one sun. We're speaking about 16 module coated on the web and measured, and we're speaking about so that we arrive close to 7% in an average, with the standard deviation that I mentioned before that is really, really small. If we take the same parameter, but we reduce in the concentration, you can see that we lost more or less 1% absolute in value. So just to mention it, how is important as well, not only the material that you are using, not only of the process, but as well, for example, in this specific case, connected to the yield, the concentration of the formulation and the solubilization of the material inside. Another part that I mentioned in the beginning was exactly the HTL, and it's possible to see that when you are using the single or the double HTL, the performance are pretty slightly different, where tendential with the HTL, you have a slightly maybe better standard deviation, but with the single for this formulation, specific formulation, this is not a general rule, but for this specific formulation, it's possible to get a better performance with the single HTL. And if we try to give a general evaluation for this kind of formulation, if we change, we take the higher concentration, so the best condition, we take the best temperature condition, and we change the substrate, just to change the substrate, similar in the sheet resistance for the IMI or the ITO, as we prefer to call. And in this side, you see that there is a main big difference. But in the other side, if we try to take as well, so different concentration and to different temperature, but the same substrate, is clear that here the substrate make the main difference, is pretty clear. And here, if we maintain the same best substrate, but we change slightly the condition, you see that there is as well this big drop. Just to underline the point that so the great results are combination of the several parameters, and as well not only in the parameter of the process, but as well on the material and the supplier that you are using. If we try to make one step forward, especially to increase the area, we are able to see that, for example, before the encapsulation in the module 3x10 and 10x10, so we are able to see that the performance, yes, is clear, start to drop slightly. This is pretty expected, especially connecting much more on the fifth factor. You see that the other parameters are more or less the same, but the fifth factor is one of the parameters that I mentioned in the beginning, that is one of the parameters drop down in the scale up. And if we try to take 4x10, this after the encapsulation, we see that there is still one small drop, but we can see that in this kind of drop is really small, and so in this kind of formulation, the increasing of the dimension is not a big issue. This means that what we achieve for the small mini module, we are able to achieve slightly less, but similar in the results as well with the bigger module. If we try to move as well in the lifetime and the stability, and so, for example, in the mechanical stress, just to see for some kind of application, this is an equipment developing internally, where we try to stress in one side, in the other side, so the maximum stress possible, the mini module. We see that after 20,000 cycle, and I remember one side in the other side, so in this case, you stress much more the mini module, the performance are pretty similar from the beginning, maybe just in 20,000 cycle, we see that there is a big drop, a slightly higher drop. But in general as well, the optimization of the encapsulation and all the layers are pretty fine in this kind of development. If we enter much more in the stability, and I believe that this is one of the pretty interesting for this kind of application, for this new generation of the production panel, is the stability. And so just to remember that tendentially the light stability is made 65 degrees C. In our case, we have 85 degrees C in order to accelerate 4 times more the degradation and to reduce the time of the test. But you see that in the best condition, so with the third substrate, with the single HTL and the Fuller and acceptor derivatives, so we see that after close to 4,000 hours is start to arrive now close to the T80. And so these are pretty amazing results after 20 years I working on the OPV. So I never seen one result so interesting, because this in a 65 degrees C we can multiply more or less 4 times more. If we think in a real world, we can speak in about much more than 5 years. The expectation will be much more than 5 years in outdoor in a tropical weather. In the other side, so for the outdoor test, just to make some comparison as well in the single and double HTL, this one was one of the first test 1 year and a half ago, so the performance was slightly lower in that era. But just to show that as well, when you want to choose as well maybe the right condition, as I mentioned more than one time, depending on the application. And so this not means that maybe to using the HTL in a single layer that you get the higher performance will be the best choice, because in this case you see that just after 30 days in outdoor exposure you can find the same PC in outdoor directly if it's single or double HTL. And so depending on the application, depending on the optimization, is possible to make the right choice for the application in itself. And we arrive in, so to moving for the production line, we can see that, so in this case, we see that, so to improve this, the area coated is clear that one of the part that I already mentioned is necessary, not only to increase maybe the concentration or to modify the concentration of the ink, but also you have clear so just to give a metric, so we're speaking about in the roll-to-roll R&D something like a 30-40 milliliter. Here in the production, tendentially we're speaking about close to 1 liter. And so it's clear that the quantity that you are using are different, and as well what you develop in a few milliliter as well, it was a big quantity for the standard R&D, for example 40-50 milliliter is so you have to remodify maybe some part in the ink using in the production, especially because you have a higher volume, and so the solubilization could be that arriving in the limit, and so you have to adapt in some way. But just to try to stay in the time, if we try to coating in a different thickness, in our production line we have a 32 line, so this graph where it's possible to see in a different thickness coating and a different test. For the measurement of the single line is clear random, is not a sequence, is a sequence but it's not all the lines. You see that are more or less pretty stable during the line and during the coating. But if you see, one of the main issue we get in the beginning was exactly, for example, the pedo thickness, that there were a big drop, especially in the center line between 10 more or less till to arrive at 20. So more or less 1/3 of the line that were receiving the less thickness of the pedot. Just to mention what we say till now, that's so it's clear when you optimize everything for the small cell, so you see the best condition, whatever the behavior, the material. But in the end, when you arrive for a realistic production, you have to maintain, or you have to take much more parameter to consider, and so you have maybe to find the right compromise in order to get a realistic product. And so this not means that you have the best performance or the higher performance possible. But in the other side is pretty interesting as well, the results that you see, for example, in the before lamination, the performance are much lower than in the R&D. This is still not the last results, but just to show the concept. But you see that tendentially for the production line, where we try to optimize is after the lamination, because we want a higher performance after the lamination. And so everything is setting not to get the best performance before the lamination, but after the lamination, is shown here. if we try to take, and this was before some optimization, but just to show that as well, the panel put in outdoor, we're speaking about half meter by half meter panel here. We're speaking, so we see that the results start to become really, really interesting, to passing the 5%, and as well, in this case, over 3 months are start to be stabilized, and I can tell you already now that this start to become stable. So in these ways, there's a pretty interesting this product, especially for the outdoor application, but as well for the diffusion light application, like a building integration. If we try to make another exercise, for example, when we try to combine different modules, just to understand what I mean module, this is one module in the panel. In this case, is a panel with the 5 module connected in parallel here. So you have a 32 line connected in series for one module, and every module connected in parallel to create the panel in this case, and the 13 module as well. You have the 13 module in this dimension, and so you see that to improve to increase the dimension in the active area, you see that there is started to be is pretty normal to start to drop the performance. So in this case, it's clear that depending on the application, and depending as well of the kind of the project for the OPV applied directly, so it's possible to choose directly the right panel with the right performance. It's also true that this panel are pretty interesting, because we're speaking about close to 6%, and now missing still some optimization from our side. So for example, to using the right substrate or whatever. And so I strongly believe that this value, especially for the module arriving to 8 modules, something bigger than this, will be possible to passing the 6% in the commercial application. Here, just to finalize, some application not with the non-full arena acceptor, because we'll be ready just in the second half of the next year, or maybe in the second trimester of this year, sorry. And so just to show some application, this was an installation in the glass with the OPV, and was the oldest application from our side. Was installed in 2016, end of 2016. Is still alive, is still producing. Here is another big facade as well. Another one, so is for example in a space open bar, especially here in Brazil, are pretty common, this kind of stuff. Here as well, another building integration. Here is another one just to show in the office. Here was a request of the client now to make a thermal isolation, and so was using the OPV in order to absorb all the infrared part, and so in that way was developed specific for this kind of application. There is as well the static. Our palm was sold around the world in all continents. Is the OP3. It's possible to recharge the phone or small devices, and you are able as well to cover the request of a router, and so to distribute as well the Wi-Fi in a square. And this means that so for the city you can design maybe your totem, and you already see to see the totem that there is maybe the Wi-Fi free in the square. In the other side as well, the mobility, and so the integration of OPV, maybe not so interesting maybe for the car, but in the other side will be much more interesting for the trucks and the buses. This was a collaboration with Mercedes, and so in this way I believe that we arrived to the end. I would like just to take 1 minute just to give a big thanks for the R&D guys, and as well the production guys for share these results, and as well thanks for your attention today.
This was amazing, Diego. A lot of great results, very clear presentation. We have a lot of questions, and we have time for a nice Q&A. Let me start with, from my point of view, the best question that I could ask. I know that you have a great experience on both OPVs and perovskite solar cells. your general feeling, your general take-home message, all the differences that you can see between the two technologies, scale-up problems, where we are going with both the OPV and perovskite PVs.
So can you say the last sentence?
And where are we going with both technology? What do you think
Yes.
about the future of these two technologies?
Look, this is a good question. So it's clear that we are working on both. We believe in both. I strongly believe that the perovskite in the future or in near future, maybe, or medium future, I don't know, will be something that's give a boost, especially for the lower price of the material. And so in that way, it will be possible for a rough calculation. I make a rough calculation, and we're speaking about already in the beginning, not for the mass production, will be possible to have 20%, maybe 30% of the cost of the silicon panel. So it's clear that there is a big gain in terms of energy cost, but it's also true in the other side that I don't know, but will be probably pretty hard to arrive in the same lifetime of the not means that this is not good, because depending on the price, if the price drop down, the lifetime is connected to the price, and so if it's cheaper, you are able, it's easier to install. Maybe so you enter inside in to make some calculation where maybe there is a big convenience to have a panel that after 5 years or 10 years you have to change respect to the against the silicon, then maybe you arrive at 30 years, but especially because you have a less volume of money that you have to apply. After 10 years you remove, but you have as well a better technology, and so in that way you have a risk in terms of fixing money in a less time and to gain. So there are several overview in terms, it's not only a technological issue, but as well politics, because just to remember that we have the lead inside and functionalize with the polar solvent, and so combined with water, and so will be an issue as well from the politics and the law. From the OPV, it's clear that I strongly believe will be a technology enter inside, because there is, for far as I know, another technology that is not toxic. It's possible to have now it's possible to have a reasonable lifetime, a reasonable performance. Is possibly easier to integrate in the building. So in that way, it's possible to find, and we see that there is a specific market that maybe other technology are not able to cover. And so I strongly believe that there is the future for both in a different sector.
Amazing. Thanks a lot. Yeah, there are a lot of questions, and the first one is probably for the beginning of your talk. They're asking you, modern devices use PIN instead of NIP. And do you have a comment why you have been showing devices based on NIP technology?
You mean for the perovskite?
For the organic, I think this is for the beginning of your talk.
No. We are using this structure just because if you are using the regular, so where there is the HTL on the bottom, so the PIN, if you want, it's clear tendentially you are using the P dot, and so it's a water-based whatever. So tendentially, we know, and this was a result that was already achieved when working in Konarka, that was pretty clear to using the same material, the same condition, whatever. If you reverse the P dot and to put on the top, you gain more or less double of the lifetime. This means just because the P dot is hygroscopic, and so in that way maintain a part of the water inside, and so the lifetime of the device start to degrade much faster if you are not putting on the top. But in the other side, the HTL on the top, as I mentioned before, give an additional gain to using the screen printing or other technique for the silver deposition, and so in that way will be impossible to using a thinner ETL on the top, and so in that way there are several reasons, but I believe that the main two reasons are there.
Makes sense. And there is another question, why you are not using copper as a top electrode?
Look, Look, copper, we tried to using in the past, but there are several, you mean for the paste. So the paste of copper are terrible, or at least till now. Tendentially, you can find on the market the copper paste, but so are terrible to using, especially in the screen printing. You trash a lot of material of the screen in itself because the viscosity and the material in itself is really bad. And so for now, the silver is the best one. It's also true that the silver is a commodity, and so it's clear that the only way to reduce the cost here today, there were not the time, but just to mention and about the top contacts, when some 4 or 5 years ago there were was necessary to give a big drop in the cost of the square meter for the OPV, and so one of the main issues was exactly connected to the silver because it's a commodity and the price is connected to the market directly. So you are not able to gain a discount connected to the volume. The only way to reduce the cost of the silver is to using less silver. And so we develop a new HTL in order to reduce the quantity of the silver and the finger of the silver. And so we reduced 80% of the use of the silver and was a big drop as well in the cost. But connected to the copper is just is not that doesn't work, but is not able to using in a market. So there is not a material able to using arriving from directly from the market in a quick way.
Yeah. They're asking you a question. I think this one is for the mini module. Why is the series resistance so large? And it seems to be the reason for the low fill factor that you have in your devices.
Yeah. Yeah, so it is not only the series, but as well the shunt. And this depending on the formulation. In this case, it's clear today I show some results with this formulation, this ink are pretty nice during the coating. And so you are able to have a slightly better shunt resistance. And so to reduce the quantity of the shunt inside. In the terms of the series, it's clear that this depending on the material, depending as well how the adhesion between the layer. And so it's clear that for the small devices in the spin coating, you are able to have a better interface between the layer and your fill factor growing up. But in the other side, and so your drop in the fill factor connected to the zero resistance is just connected to the resistance, intrinsic resistance on the material. When you are going for the increase in the area, it's clear that it's impossible to maintain the uniformity and the right adhesion everywhere in a big area, because we're speaking about so from nanometer to meter. So in that way, is not only one magnitude, but is 4 or 5 magnitude more. And so it's clear that this create some not right interface or not right contact between all the layer, and this reducing the series internally.
Yeah. This one is a great question, I think, from Lucas. They are asking you, there are several techniques, vacuum-based techniques that are used as industrial process. And he's asking you if this sputtering or evaporation could be suitable also for organic solar cells.
So no, I'm not catching so is to using the sputtering in the solar cell?
Yeah, sputtering or evaporation can be used for organic solar cells as well. I think they are referring to the fact that the deposition technique as vacuum-based deposition technique are used for OLEDs, and they are wondering if they can be used also for OPVs.
Yeah. No, of course, if you evaporate, you have pretty better results because, as I mentioned, the first parameter you are already increasing is the fill factor, because the adhesion, you can decide the rate of the deposition, whatever. And so, and one of the example is the Heliatech leading the OPV by evaporation, and their results are much better than not maybe the coating. It's also true that what we are looking for is OPV is one of the technology we are developing. We strongly believe in order to reduce the cost, we are just in the beginning of the story. It's clear that the best results maybe you are able to achieve by evaporation. You mentioned the OLED is one of the big demonstration, but it's also true that it's necessary to have a much higher investment in the beginning, and you have to optimize as well the process in some way, because in our case, if happens something, we are able in few seconds to re-optimize everything, continue to coating. With evaporation, it's clear that you have to remove the vacuum too. So in that way, take much more time, and the OPEX start to become higher. It's clear that if you have everything optimized, you have a big investment. We're speaking about $1 billion, like, I don't know, Samsung, LG, or whatever that are making, for example, the OLED. Maybe you are able to make something much better. It's also true that Eliatech make a really nice panel, and with a higher performance need like us to create the market. And so in that way, I'm not seeing this level so big difference in terms of economic value.
Another one here. Can you please identify the main causes of device degradation, especially under indoor accelerated lifetime and outdoor performance evaluation? Which are the dominant causes, temperature of light, for performance losses in your case?
Look, tendentially as well for the perovskite. So, for example, I don't want to make a general because it's not true, depending on the composition, that there are several variables. I believe that was pretty clear in the presentation. But in general part, tendentially the light is the higher killer. So it's clear that we're speaking about organic material for both for OPV, but as well for the perovskite, because there is organic inside, if it's not specific, just full inorganic. So tendentially with the ultraviolet is one of the accelerating degradation. It's true that speaking about of the organic, the oxygen is one of the big killer, but if you improve, if you have a good encapsulation, is become not a big issue. And as well the temperature, we find some solution that is possible to reduce this dependence. Just to give a number, our perovskite panel, that is more or less 300 millimeter by 300 millimeter, so it's still small, but under climate chamber 65 degree 65 degrees C, 85% relative humidity, we're passing 4,000 hours without any kind of issue. So in this case, for example, the temperature is not an issue. Tendentially, the OPV as well is not an issue, but depending on the composition. And so, but it's possible to tuning in order, again, as I said before, we have a different for the silicon that is just one atom, one technology. In this case, is a family of material for both perovskite and OPV, where it's possible, depending on the application, to have the right panel in order to reduce the negative effect. But just to try to answer, and I don't want to avoid the question, but I strongly believe that's one of the main issues connected to the light for both technology.
Yeah. There are many other questions. Let's go faster.
I don't know if it's good or...
That's amazing. Thanks. Could you describe the burning characteristic a bit more in details? What is going on? Does a customer need to take any step to deal with it?
Yeah, this is a good question. Tendentially, when we sell something, we're speaking about we are not using the T80, but we are using the TS80. So what means that the T80, you starting from the beginning, you have the drop till to 20%, but we are starting to calculate, and this happens as well for the silicon with other technology. Tendentially, when start to stabilize, in that way you start to calculate the T80. And so for this is called the TS80, because because it's the stable 80%. So just to try to answer this big barn, tendentially in general way, and again, depending every time from the single case, but in general way, tendentially is an arrangement of the layer inside. And so tendentially, when you start to expose to the light, to the temperature, to the humidity, whatever all the condition, the layer that are maybe, I don't want to say rigid, but start to modify, and so you have start to have maybe a drop in some way. It's not always happen a drop, but in some characteristic, and so maybe someone older like me, maybe you, Daniele, remember that, for example, the Ph.D, there were burnouts in some way. The standard. So just to say that there is not a rule, depending, but tendentially in a arrangement about the material. There are some other stuff connected maybe to the Fuller and acceptor, in particular for the PCBM, for example, that there is a dimerization inside and there is as well a big drop inside, but this can happen as well later. So tendentially, when in the stability you have the big drop, that's is the burn-in, and after there is a second big drop where fail the barrier. I don't know if I answered to the audience, but
Yeah. Okay. Will you share any details on the capsulation method and materials that you used?
Yeah, clear that I'm not able to share, but I can tell that tendentially for the OPV, tendentially we are using, like everybody, I believe, the epoxy UV curable, and so in that way it's possible to start in the curing of the epoxy just to expose in a few ultraviolet, yes, to the UV, and after to finalize with the temperature or room temperature, and with the barrier depending as well which kind of barrier, because there are premium barrier, basic barrier, whatever, and so there are several characteristics, but in general way, so it's necessary to maintain less pressure possible, and so for the OPV, tendentially the epoxy adhesive is the main used. For the perovskite, unfortunately, we make a publication 1 or 2 years ago about this, connected to the encapsulation of the perovskite. This is a pretty an issue, because the epoxy, but as well the other kind of adhesive, eating in some way or destroy the perovskite. And so for this, we started more than 1 year ago a couple of collaboration with some big company around the world, exactly to try to develop one specific adhesive for this application. Just to mention that it's clear that if you want to make the perovskite under the glass, maybe it's not an issue because you are able to make in the edge sealing, and so there is not direct contact. But in our case, we want to arrive for the flexible perovskite, and so you have to cover all the surface with the adhesive, and so the direct contact there is. Sorry, I'm not able to enter too much in detail in
Sure.
some stuff, but in a general answer.
Let's go with the last one. You mentioned 85C aging being 4 times faster than 65C. Did you observe an erroneous behavior of the lifetime?
No, this is clear. Is a metric. Tendentially, this was used as well. I remember in Konarka, that was this kind of rule was much more connected to the P3HT. Maybe with the new material, is not exactly this kind of rule. But just to mention that tendentially, when you are improving the temperature, you degrade faster, and so tendentially, so is connected. That's 5 degree more degraded too fast more, and so in that way it's clear that the 85 degrees C is just from our side in order to because every equipment has a cost, so much more variation we have to do, we have to testing, and the space that you have is not so much, and so tendentially we try to accelerating in order to reduce the time. It's true that now the time is start to become absolutely interesting, because when we're speaking about 4,000 hours are a lot of time, so we're speaking about really month, so close to a year. So in that way, we try to use in this accelerating aging test exactly to reduce the time and to make an evaluation before to put in outdoor. But I would like to underline one point, that the accelerating aging test is just how to say, it's just to give an idea to comparison, because when you apply in outdoor, there are several other combinations, and there is till now a relationship between the results in outdoor and indoor. And so in that way, till that you are not applying outdoor, you are not totally sure what's happening. This I can tell you that I have several examples in my life to show that there is not this correlation. So for this, we starting this year a new project exactly to try to using the artificial intelligence with the 10 years of the results in order to find, I don't want to say a correlation, but at least something that is possible to join and to have a prevision of what's happening in the application outdoor.
Amazing, Diego. Thanks a lot for sharing all these experiences with us. Now we are almost done with the time, so I would like to conclude this webinar. I'm very glad that we are still in contact with you as Fluxin. Hope we will still do some simulation for the upscaling of these devices. And thanks a lot for everyone that's joined this webinar, and we will see you the next time. Thanks again, Diego.
Many thanks for your invitation. It was more than a pleasure.